So, first of all, I'd like to thank the organizers for giving me this opportunity to present my work over here. And I'm also grateful to my previous speaker for finishing well ahead of time. So, I mean, since morning, we have been hearing a lot about defects and disorders and how to get exotic states of matter out of them. We'll be going in a completely different direction. We'll try to see in ultra-clean graphene how we can talk about the quantum critical conductivity in these kinds of samples. So let me talk about a tale of two graphenes. On one hand, you have what is called the theorist's version of graphene. It's like pristine, clean, no disorders, defects, and impurities. It can be described as a clean electronic system. On the other hand, you have what is called an experimentalist version. It's like lots of disorders, defects, impurities, and at the end of the day, it just gives you a disorder or a diffusive electronic system. The main difference in physics in these two kinds of systems is the fact that a clean electronic system can host momentum conserving collisions, such as electron-electron collisions. The same sort of momentum conserving collisions are not found in a disordered system because it gets suppressed by electron impurity scattering and electron phonon scattering, which are momentum relaxing collisions. Obviously, as a result, experimentalists are extremely interested in working with clean systems because these clean systems can actually give you strong electron-electron correlations, but without the help of any kind of Middey potential. So you get the exact same physics that you get in twisted systems, but without any Middey potential. And in this case, the stronger electron correlations are actually driven by something called electron hydrodynamics. It's a hydrodynamic regime in which the electrons move like a fluid, and the electronic behavior can be aptly described using an electronic version of the Navier-Stokes equation. Some common physical features that you find in electrons that obey this Navier-Stokes equation is that you don't have randomly popping electrons moving here and there. You rather have a parabolic spatial dependence of the current. You also have like electric field lines bending in if you have like a constriction in your channel. These are some common hydrodynamic features in electronic channels. But what makes graphene so interesting? The fact that graphene has this unique band structure which hosts massless Dirac fermions. So now, if you plan to take your Fermi energy from the valence band to the conduction band, you cover this entire phase space with a Fermi liquid regime. But when you are exactly at the Dirac point and your Fermi surface is almost not there, you have this beautiful region of space which is called a Dirac fluid. And it has been theoretically explored almost like for the last 10-15 years. One of the fascinating theoretical expectations is that a Dirac fluid substance can actually have the minimum viscous dissipation of any condensed matter system in all. And this is given by some kind of a holographic bound, and we are going to come back to this in a later stage. But people have already started working on this for the last 10 years. So people have found like violation of Mahadevan-Francis law, negative local resistance, Mott formula has been violated, they found superballistic conduction, Planckian scattering, the Poiseuille flow that I was talking about, where you see this parabolic dependence along the width of the channel. They have found energy waves, Charvin resistance, getting mixed up in Corbiner geometry, and even imaging of electron vortices. People have found a wide range of exotic physical features in these kinds of systems. But one thing that people have not yet exactly talked about is something that has been theoretically actually predicted long time back. It's the quantum critical conductivity, the sigma Q. So it basically says that if you have a system which has a Fermi surface, or even if it doesn't have a Fermi surface, the intrinsic conductivity of this kind of a Dirac fluid is given by 4e squared by h. The main experimental problem why people have not been able to found it is basically that you have a lot of disorder in the system and you are unable to exactly come down to a limit where you can actually measure this value of conductance. So we took a three-pronged approach. We decided that we are going to make samples, clean samples with large momentum relaxation length, larger than the dimensions of the sample. So that goes out of the picture, at least one length scale out of the picture. We are going to measure the electrical conductivity, we are going to measure the thermal conductivity, and we should be able to make a comment on the quantum critical conductivity in these kinds of systems. And that inspired us to make samples of this kind of architecture. I'm not going to go into details of this architecture because it's going to take time. But if I have to talk about the kind of impurity concentration that these devices give, so over the years, people started with like 10 power 12 per centimeter square of defects when Arindam discovered graphene. Around like 2010 and all, when boron nitride encapsulation actually improved this impurity concentration to around 10 power 11, people made these unique hydrodynamic geometries, which actually brought it down to 10 power 10 and even 10 power 9. And there was work including like suspended graphene as well, which was able to like bring down the impurity concentration further down to around 10 power 9. And our samples actually lie in this range of 10 power 9 to 10 power 9. This is one of the cleanest samples for materials with substrate non-suspended, in which you can do gate field applied physics. For some of these samples, this is how the transfer characteristics looks like around 100 Kelvin. Now, all these samples have different impurity concentrations. As you can easily understand, the cleanest samples are the ones at the bottom. You can clearly see that at high Fermi energies, at high number densities, the resistance goes almost to 0. And the peak at the center is almost extremely sharp. If we try to explore this region where we have this Dirac point, something that is very fascinating is from the disordered sample to the cleanest sample, you see that the conductivity depends on the number density, like from a sublinear dependence to a linear dependence to a quadratic dependence and so on. So obviously you do understand that as we are going from a disordered sample to a clean sample, there is a dependence on the number density which actually decides whether you are in the hydrodynamic regime or not. And that basically leads us to try and understand the electronic phases that one can have in ultraclean graphene. So we start with the disordered phase at the center. So we are at the Dirac point, there is no Fermi surface, there is disorders, and whatever gate electric field you apply, the conductance does not change. You increase slightly and now you see that, okay, the conductance is increasing, but this is not because of the gate electric field, this is because of the thermally excited holes and electrons in the system. And this can be easily checked by measuring the N-min or the impurity concentration in your system as a function of temperature, and it shows this beautiful quadratic dependence. Further down the line at higher densities, you have the Fermi liquid behavior, where at extreme high densities, we have been able to even see the Charvin resistance, Charvin conductance. And within this Fermi liquid regime, we actually see a fantastic crossover from viscous to ballistic over a wide range of samples. Now you may ask this question that, fine, LEE is basically your electron-electron scattering length. When that length scale, which is the main interaction length scale in our systems, when that becomes greater than your width, then obviously it's a ballistic sample. But when it is less than the width, how do you conclude it's viscous and not something else? The main reason behind is multifold. So first of all, if you are looking at a diffusive system, the conductivity does not depend on the dimensions of your sample. If you're looking at a ballistic system, it depends on the length of the sample. But if you're looking at a viscous system, the conductivity has this peculiar quadratic dependence on width, which we are easily able to see in our samples. Second of all, moving in the exact same direction, we also see a fantastic n-square dependence in our sigma, which is exactly what you see in this formula as well. And very close to the Dirac point where you find that the viscosity becomes an intrinsic property of a system, does not depend on the number of electrons that there are. You find this fascinating n-square dependence. Further down the line, when at extremely high densities, it converges into a linear in n dependence, that's when the viscosity, the shear viscosity actually starts depending on the number density as well. Also following in the same line, if you now calculate the kinematic viscosity from this shear viscosity, it more or less aligns with the theoretical expectations from around 0.5 to 2 meters square per second. And last but not least, we have also done differential resistance measurements. And what we see over here is this beautiful double peak with a valley at the center. This is a signature of hydrodynamics. I'll just quickly explain what this means. So this central region, which is referred to as a Knudsen regime, when you're actually increasing the bias in your system, or the J, the current density, as you're increasing the current density, you're increasing the energy of the electrons, which means you're decreasing the mean free path of electron-electron scattering, or the LEE. The LEE basically comes down. Now, because this is a very low temperature data, so this is the data where the LEE by W is already greater than 1. And however bias you apply, the LEE never becomes less than the width of the sample. So the only scattering happens at the edges of the sample, and as a result, your resistance increases. But once you have applied sufficient bias to make the LEE become equal to W, now you start having the momentum conserving collisions. And so that does not contribute to resistance, and you easily see that the resistance actually starts coming down now. And this is known as the strong Poiseuille regime, which is the fluid regime. And at sufficiently high temperatures, you see that this dip actually vanishes and you just have this fluidic behavior. Now, I hope that I have been able to successfully convince you that we have a fluidic flow in our system. We go into the thermal transport where we do Johnson noise thermometry. I'm not going into details, but we just measure the Johnson noise in the system and we try to calculate the electronic temperature. So we apply an electrical field and we measure the temperature, and we see that, okay, the temperature scales linearly with electric field, but the slope is inversely proportional to the square root of the Lorentz number. As we check across the entire phase space from like Fermi liquid to the Dirac point, we see that the slope of this line actually keeps on decreasing, which basically means that your Lorentz number is increasing. And this has this fascinating kind of Lorentzian shape, which cannot be explained by Fermi liquid theory. But fortunately, it can be explained by this Dirac fluid model, which has been explored beforehand. And not just this sample, in different samples with disordered, with higher proportion of disorder also, we see that this model holds, but just that the range over which this is applicable comes down a little bit more. We see that at all temperatures that we have probed, roughly from 19 Kelvin to 260 Kelvin, we see the data matches pretty well with this model. And we have been able to calculate the entropy as well from this formula. And fortunately, we see that the entropy in the thermal carrier regime, which is from roughly around from 80 Kelvin to 300 Kelvin, it actually matches this T-square dependence. So electrical conductivity done, entropy done, last thing is the thermal conductivity. And we find that the thermal conductivity has this standard number density dependence as expected from the Lorentz number variation. And what we see is that the thermal conductivity and the electrical conductivity have this inverse scaling. Again, this inverse scaling is also a critical experimental signature of the fact that Wiedemann-Francis law is no longer valid. Your electrical conductivity is no longer decreasing at the same rate at which the thermal conductivity starts increasing near the Dirac point. With all this information, we now set up calculating the quantum critical conductivity, and we find that sigma q has this very beautiful behavior, whereas at 110 Kelvin you see there is a number density dependence, a very nice number density dependence from like 0.1 e square by h to around 4 e square by h. But as you keep on increasing to higher and higher temperatures, you come closer to room temperature, you see the curve becomes more or less flat. And the beautiful thing is, at low temperature, you might have this degeneracy or discrepancy in the value of sigma q. You're like, depending on the number density, you have a different value of this quantum critical conductivity. As you come closer and closer to room temperature, you find whatever be the value of your number density where you're at, or wherever the Fermi energy is, you're actually having the same value of quantum critical conductivity. This suggests that this quantity actually is independent of the Fermi energy of the system. And we also find that this quantum critical conductivity has this beautiful, universal nature across all temperatures and devices that we have measured. And also, like, whether it's in the valence band or the conduction band that we are trying to check. We don't understand this thing, to be honest, if at all there is any kind of universality over here, but it's something that we are still trying to look at and understand. So this is the 4e square by h picture. The last part of the picture is what I told about initially. How perfect is the Dirac fluid? As we mentioned, that the Dirac fluid in ultraclean graphene is supposed to harness the minimum viscous dissipation that is possible. It's given by this lower bound, holographic lower bound of h cross by 4 pi kb, which again has been theoretically postulated and experimentally found to a certain extent by people. And our experimental results actually show that for our cleanest sample, we are able to come to an order of 4, a factor of 4 of this holographic lower bound, which is extremely close. And we also find this fascinating correlation between the cleanliness of your sample and how close you're able to come to this holographic lower bound. We believe that if we can actually improve on the cleanliness of the sample even further, we can actually be able to hit that lower bound. So finally, conclusion. The take-home message, we have been able to fabricate and reproduce high-quality graphene samples. Again, high quality is a very relative term. So to be quantitative, we have made extremely large electron mobilities of the order of 5 × 10⁶. That's the highest mobility we have reached at room temperature. And we have found, we have ensured that the momentum relaxation length in all these samples are greater than the dimensions of the sample. And at the end of the day, there has to be a strong Poiseuille flow. Secondly, we see this inverse scaling between the electrical and thermal conductivity, and it can be explained using the Dirac fluid model, which again states that we see the Wiedemann-Franz's law violation. We also have the experimental observation of the quantum critical conductivity of the Dirac fluid in graphene. And last but not least, we also try to show that cleanliness can be used as a tuning knob to modify the viscous properties of the electrons. Finally, I'd like to acknowledge all my experimental collaborators and theoretical collaborators, Subrata and Nisarg, and thank you for your attention. Estimated means like from our number density
measurement,
and,
yes.
Yeah, number density and temperature values, we have calculated that.
I see. What is the typical length we have?
So it roughly varies, like over the thermal range that we have tried to work mainly. It roughly varies between around 400 nanometers to around 600 nanometers.
Right. Okay. One more. When we do for the electron hole region and hole doped region, right? For the hole doped region, you have also PN junction, right?
Yeah.
Just because of the contact.
Right.
How do you take into account that?
But we actually, for some reason, over the multiple devices that we have measured, we do not see any prominent effect in the results of the presence of any PN junction. We do see that there is an asymmetry in the results. Don't know if we, like you can to a certain extent see over here that the hole dope side and the electron dope side do not exactly reflect the same values, and it's slightly asymmetric. So that's why we try to talk about the hole doped side and the electron doped side separately. We don't talk about the entire pictures simultaneously. But yeah, obviously the PN junction is something that needs to be taken into account.
Okay. Thank you.
Yes.
So only one thing I could not understand, why you are calling this as quantum critical conductivity, because you are doing these experiments at finite temperature.
Yeah.
So
that is a nice question actually. So I mean, technically quantum phase transitions you expect at t = 0, right? And basically what you are trying to see over here, the Dirac point, again there is a lot of controversy in theory regarding this. I wouldn't want to take any sides, but there are certain controversies whether you would want to consider Dirac point as a quantum critical point or not. But mainly what happens is this physics is something that should be observable at t = 0 as well. It is simply because of the presence of disorder that you don't see that, and you have to resort to measuring these things at higher temperature, and then you see this physics. It's just for like from an experimentalist point of view, to get the results, you have to do this at a higher temperature. You cannot go to sufficiently low temperatures. But if essentially we are able to get any particular system where it is so clean that disorder physics does not come into picture at all, even if we go down to say 4 millikelvin or something like that, we should be able to actually see the same sigma q values at that low temperature.
okay.
How high is the phonon contribution to thermal conductivity?
Yeah, right. Nice question. So the electron phonon scattering, for some reason we don't see the contribution of that in the rho versus t or I mean the temperature dependence of resistivity or something like that. We are still trying to understand if at all the electron phonon contribution is fudging the data somewhere or somehow otherwise, because mostly whatever signatures we are seeing, these are like non-Fermi liquid with the rho going as T square and so on.
The question was about thermal conductivity.
Oh, okay. Can you just rephrase one second?
Yeah, how large is the phonon contribution to thermal conductivity?
Okay. So whatever we have measured, these are just electronic contributions. We have not looked at the phonon contributions. Particularly, if you look at the temperature data that we have taken, is the electron temperature in particular. So it gives you just the electronic thermal conductivity. It gives you no information about the phononic thermal conductivity. And over the range of temperature, like from around 19 Kelvin to 100 Kelvin, where we see the fantastic agreement with the Dirac fluid model, the phonons can largely be considered to be like frozen. So yeah, I mean at higher temperature, again, we are still trying to understand how the phononic contribution will be, the electron phonon interaction will be like in these kinds of systems. But yeah, right now we don't have much information about it.
I have a question.
Yeah.
So how do I think about electron scattering if there are no lattice defects and if the field is uniform, right? So then I would think all the electrons would feel the same force and there'd be a laminar flow. What would cause one to accelerate or to bump into another or feel the field and scatter?
Right. So usually, like when you have this diffusive system, I mean, when you apply an electric field, whatever the electron experiences is something like a mean field. Like you have this electron impurity scattering, and after the scattering, it's something like a Brownian motion you can consider.
Yeah.
But when you have this clean systems,
right,
the electrons are now entangled with each other as well. There's a strong interaction between them. And now the electrons that are
entangled meaning, so you're talking correlation?
Correlations, yeah, correlations. The nature of the correlations, again, it's not very clear. Just Coulombic interaction should not be the entire picture. There should be something else as well. But the electrons that are residing along the edge of the channel, they experience some kind of viscous force which is not there at the center of the channel.
Okay, I can understand the edges scattering.
Exactly. So that's how you get this kind of a parabolic dependence of the, parabolic spatial dependence of the current when you are applying an electric field.
So it's dominated by the edges then?
Not dominated by the edges. The edges basically restrict the electrons over there. So you have some momentum relaxation there. But the electrons at the center, they do not feel that because they are having momentum conserving collisions with the electrons just nearby. So those electrons have, they have a larger current is able to flow through the center than along the edges. There is a particular term which is used for this called no slip condition. The electrons along the edge, they don't slip. So there is no friction along the edges. So that's one particular condition that people usually assume when they talk about these hydrodynamic electron systems.
I see. So what's the scattering time or scattering rate?
It usually varies. It's less than 1 picosecond, obviously, which is the electron phonon scattering length, scattering time scale. Roughly, it's of the order of hundreds of femtoseconds.
Okay, I see. Thank you. More questions? If not, let's thank our speaker for a great talk.